Anybody have any homework problems you want to see? There was one I wanted to talk about. I only gave you two, I think, but one of them. So let's talk about number one. Okay, so so the left member has an angular velocity of +6. So this thing's getting taller. So this is in linkages number 1. And this thing's forming an equilateral triangle at this instant. And this one's going this way, this one's going this way. So let's just think about like how this is going to develop, how many equations you're going to get, constraints and stuff like that. 120 and 100. Okay, so first of all, how many equations are you going to get from Newton's laws? Yeah. So you're going to get one equation for, let me call this 1 and 2. And let's call these joints A, B, C like this. So from body, was that champagne?
No.
So from body 1, we'll just get one equation. The moment equation. From body 2, there's no fixed point on body 2. And so we're going to get 3 equations. Those are from Newton's second law and the moment equation. And how many variables do we have at this point? So we have, so the way it's going to work out is, since we're only using the moment equation for body 1, we're not going to see the reaction forces at A in our first pass through the equations. You might come back to that later after you're all done, depending on what the question asks you. But there's not going to be any, let's call it RAX or RAY. There is going to be an alpha 1. There is going to be a reaction at B, so that would be the force on 1 by 2. And then for member 2, we are going to use Newton's second law. There is going to be an acceleration of the center of mass of body 2. And there's going to be an alpha for body 2. Okay. And then this one, since our about point for body 2 is going to be at center of mass. Okay, with me on that? The reaction force at C is going to produce a moment. Well, I guess we're doing Newton's second law anyways, so just because of that, we need it. So anyways, we have to think what type of force would apply to body 2 at that point C. If we're assuming that's frictionless. What's the direction of that force? Do we know it? Yeah. Yeah, it's just going to be an upward normal force. So I'll call that RC, and it's just a scalar. So we got 4, 5, 6, 7. Okay. So we have 4 equations, 7 variables. And so now we have to think about the constraint equations. So the first one is familiar. It's like the example we did last time. We're going to say that the acceleration at B according to body 1 is equal to the acceleration at B according to body 2. Okay, so how many constraint equations is that?
2.
2, yep. And so we need one more. And where's that last one going to come from? That's the one that didn't show up in the example we did last time. Well, the last requirement is what can that point, the point on body 2 that's at C in this picture, what can that point do? It can go side to side, but it can't go, well, it definitely can't go down. And we're going to assume that it can't go up either. If that ends up being wrong, then we'll have to adjust our thing and move on from there, probably redo the problem a little bit. How would we, okay, so first, before I lose the thread. So our second constraint is going to say, okay, so this one, this gives us 2 equations. And our second one is going to say the acceleration at C, y component, is equal to 0. It can accelerate side to side. It can accelerate along the surface, but it can't accelerate up and down. Okay? How would you deal with the fact, so I'm treating this as if, I could have done that as a pin in a slot joint. That's how we're treating this. It's exactly the same. But there's a case where it wouldn't be the same as that. So how would we know if our solution to this problem, like right now we're requiring that if this was going to jump up into the air, the ground would pull it down to keep that vertical acceleration 0. How would that show up if we we don't want that solution. The way it's drawn, the ground can't pull on it. How would we know that we had to modify something? Yeah.
If the force applied by the ground is in the negative.
Perfect. Yep. If we go through this whole solution and we get that force RC is negative, then that's saying it's pulling down. Okay. Well, that's not happening, and then we have to redo the whole problem without an RC there and without a constraint at that spot. Okay. Are you with me on that? There's no way to build into the problem that you can only have an upward force, Yep.
But at that point, you only have 6 unknowns.
Yep. That's right.
That's weird. It's
Well-
nice that it works out.
It always works out. It is cool, yeah. Because you lose one constraint equation, but you also lose that RC. And so it always works out. It works out because those forces, like that RC, is what enforces that constraint equation. If you lose one, you lose the other one. Yeah. Has anyone done that problem yet? Oh, yeah. And did you think through it basically that way?
No, I got it wrong, and I
Okay.
submitted it because I didn't want to do it again.
I hear that. All right.
Oh, I messed something
That's a
up.
0.
I was like, how?
No, I'm just
I shouldn't have said that.
No, what?
I was counting my variables and I was like, what did I do wrong?
Oh, yeah. Right. So that's how you have to do problems like that. We'll do one like that too. But we're going to do this 4-bar linkage one first. And the one that I drew, this body, I showed this last time. And this one always, that fourth bar always has to be horizontal in this picture. Whoops, I missed. Okay. But generally that's not true. I wasn't sure last time if it was true. I never really thought about that before. This one, no matter what you do, this one stays parallel. That's just because the fourth body always stays parallel, or the first body or whatever, because it's round. And this always has to be a parallelogram because those lengths are the same. If those lengths are different, they can all work around. Not work, but it's not necessarily a parallelogram. Okay, and we're going to calculate the acceleration of this point P. And I'm going to call these body 1, 2, and 3. It's a 4-bar linkage because the ground is the fourth. And at the instant we're doing this calculation, these are 30 degrees. Well, that's not a very good picture of 30 degrees, but what are you going to do? And the way we're driving this system is with a couple like this. So you can think of like any time you have like a machine where the externally applied load is a couple, you can think of that as a motor applying that. Okay. And we are, the lengths of all of these are 1 meter. This is also 1 meter. And the masses are 5 kilograms. And we want to calculate the acceleration of that point P. Any questions about the problem? Okay, so we talked about this last time. I think it's a nice way to think about it, to remind yourself what to expect. Anytime you can, on any complicated problem, if you can tell yourself, if you can figure out what to expect, you have sort of a sanity check on how things are going. So, okay. On body 1, how many equations are we going to get? Yep. 1 equation because there's a fixed point. How many variables are we going to get? There's an unknown reaction force at this point. Let's call that A, P, B, C. There's an unknown reaction at A, but that's not going to show up in Newton's laws equations. And the reason for that is we're only using the moment equation, and our about point is A. So anything happening at A isn't going to show up in the moment equation. Okay. We do have an alpha, and we do have an unknown force on 1 by 2. So we got F12 and alpha 1. So that's 3 variables. Then body 2, is there a fixed point on body 2? There's not, and so that's going to be 3 equations. Do we have any new variables from body 2? Yeah, we have the force on 2 by 3. We also have the force on 2 by 1, but that's just negative F12, so that's not a new variable. Are you with me on that? Then we also have the acceleration of body 2 and the angular acceleration of body 2. And so that's 5 more variables. So things are looking really bad for the good guys at this point. We have 4 equations and 8 variables. But eventually it has to start catching up, you know? So body 3, does that have a fixed point?
Yes.
Yep. And so we're only going to have 1 equation. The force on 3 by 2 is not going to show up because we've already defined F23. Okay? So that's a Newton's third law pair. The reaction force at C isn't going to show up because we're only using the moment equation and our about point is at C. And so this introduces 0 new variables. Yep.
Want to introduce alpha 3?
Yes. Thank you. You are right. Alpha 3. So 1 variable. Okay, so we just broke even on that one. That still doesn't seem so great. But now the constraint equations are where we can make stuff up. We have, we're not making stuff up. We're catching up the variables with the equations. Okay, so we have, what do we have? 5 equations, 9 variables. And so we need 4 constraint equations. And where are we going to get those? Well, the acceleration at P, according to body 1, is equal to the acceleration of P according to body 2. That's 2. And then the acceleration of B according to body 2 is equal to the acceleration of B according to body 3. That's 2. And so we end up with a system that we can solve. Yep.
Do we know alpha 2 is going to be 0?
We are, I don't think there's any way through the, I don't think there's any way to see that immediately, like in your system of equations. I think you just want to calculate it, but I would just use that as like a sanity check, you know? Yes. I can't think of any other way to squeeze that into the equations usefully, really. I mean, I guess you could make it I don't know. Let's look when we get there. Okay, so the approach is we're going to start with body 1, go through the equations, body 2, body 3, then we'll go to the constraints. Why don't you take a few minutes And if you want to work together with people, feel free. But we'll start with body one. I'll give you a couple minutes, then I'll go through. Okay, so fixed point or no?
Yes.
Okay, so it's fixed at A. And so we want the moment of inertia about A. That's 1/12 times the mass times the length squared. And then you have to use the parallel axis theorem. So that's plus 5 times. So to use the parallel axis theorem, we want the distance from the center of mass to our about point. So that distance is just 0.5. And what do you get for that?
1.67.
0.67.
Sorry, 1.67 is what I got.
Oh, okay. And that's probably repeating, right?
Yes.
And now free body diagram. We have a weight down at the center of 49.05. We have the reaction here. I'll call that RA. And then we have the force on 1/2. Anybody have any questions about that free body diagram? Okay, well, our about point is, yeah. Oh, yeah.
Adding the parallel axis theorem, we do that again, why? I'm just trying to.
Oh, yeah. So the formulas you get for these members are always about the center of mass of the member. So anytime the about point is anywhere other than the center, you have to use the parallel axis theorem. And what you're doing in every case is multiplying the mass times the square of the distance that you're moving from the center. Okay, so since we're moving, if you start at the center and move to that point A, you're going half the length of the thing, and so that's why the distance is 0.5. Okay, so let's start at with this force RA. That's at the about point, so rho is 0. The force is RAX, RAY. Cross product is 0. Then the weight force, that is negative 0.433, positive 0.25. Force is 0, negative 49.05. And the cross product is 21.24. And then F12, the rho vector, remember that's the vector from the about point to the point where the force is applied. So that's negative 0.866. Positive 0.5. The force is F12x, F12y. And the cross product is negative 0.866 F12y minus 0.5 F12x. Since there's a fixed point, we don't need Newton's second law, so we just go straight to the moment equation. And we get 21.24 minus 0.866 F12y minus 0.5 F12x is equal to the mass moment of inertia, 1.6 repeating, times alpha 1. And so our first equation says, I'm going to put them in sort of an order. I guess I'll go negative 0.5 F12x minus 0.866 F12y minus 1.6 repeating alpha 1 is equal to minus 21.24. So that's our first equation. And when I was, when we were, thinking through what to expect, if you look at body 1, you think, okay, what forces are acting on body 1? We're going to see it in the free body diagram. There's F12, and there's this reaction force RA. But notice I didn't put that in my list of variables here, because I knew that since there's a fixed point on body 1, we're not using Newton's second law, and that force is acting at the about point. Yep,
What happens if you try to use the Newton's second law equations?
it's fine.
Did they just not tell you anything, or?
It'll give you the, so it'll give you more variables. I mean, in this case, you would get the two new variables, RAX and RAY, and you would get the new variables, A1X and A1Y. But then, since you're not assuming that those points are fixed anymore, at the end, you need constraint equations that said acceleration at A is equal to 0 and acceleration at C is equal to 0. And so you'd get these 4 new constraint equations that I'm not seeing how they cancel out right now. But yeah, you could do it. It would just be more variables, more equations, more constraints.
Okay, so you ignore the Newton's second law, and you can ignore the constraint equations at the fixed points.
Right, right. Because, I mean, we sort of enforce those constraints when we say the acceleration of P is just purely in circular motion about A later. Okay, we don't say it's in circular motion about A, and A has this acceleration that we don't know. Any other questions about that first body? Okay, body 2. So take a few minutes and work through that one. So body 2 is the horizontal one. Oh, also, I didn't say this. I did say this on our last class, but this is starting from rest, which just, that's not going to come up during the Newton's law stuff. It's going to come up when you're calculating the accelerations later in the fact that the angular velocities are 0. Okay. So this is the horizontal member. We have a weight force of 49.05 at the middle. Over here we have the force on 2 by 1. Newton's third law says that's negative F12. And then over here, we have the force on 2 by 3. And I'm going out of order here. So let's pretend I went in order. Does this have a fixed point?
No.
No. And so we want the moment of inertia about the center of mass. So that means, in this case, we're not going to use the parallel axis theorem. This is just 1/12 times 5 times 1 squared. So that's 0.416 repeating. Our about point is at the center. So I guess I'll start with the weight. The row vector is 0. The force is 0, negative 49.05. Cross product is 0. Then negative F12. The row vector, that's the vector from the about point to the point where the force is applied. So that's negative 0.50. Force vector is negative F12x, negative F12y. Cross product is 0.5 F12y. And then the last one is F23. Row vector is positive 0.50. Force is F23x, F23y. Cross product is 0.5 F23y. There's no fixed point here, so we're going to use Newton's second law. And it says 0, negative 49.05 plus negative F12x, negative F12y plus F23x, F23y is equal to the mass, 5, times the acceleration of the center of mass. We'll call that A2. So that gives us a second equation, negative F12x plus F23x is equal, let's rearrange it. So minus 5A2x is equal to 0. Then third equation says negative F12y plus F23y minus 5A2y is equal to positive 49.05. And then the moment equation says 0.5 F12y plus 0.5 F23y is equal to 0.416 repeating times alpha 2. And so the fourth equation says 0.5 F12y plus 0.5 F23y minus 0.416 repeating alpha 2 is equal to 0. Any questions about that? For horizontal members like this, it might occur to you that you can skip some steps and save a little time if you want. I mean, the only forces that are going to produce moments here are vertical components. So you could just do this as, okay, my about point is here. If we have a downward force of F12 or an upward force of negative F12, that's going to produce counterclockwise moment. An upward force of F23y is going to be a counterclockwise moment. You can skip the table and do it, but on tests, I'll always give you time to do the full table, full thing. In my opinion, the best way to do it is get used to the full method and just do everything fully until you just kind of naturally start skipping stuff because you're used to it, you know. I think that's better than doing shortcuts from the start. Okay, 4 equations now. So now we're on the last body. So take a few minutes and work through that one. So is there a fixed point on this?
Yes.
And so we want the moment of inertia about that point C. And so that's 1/12 times 5 times 1 squared, plus the parallel axis theorem part, which is 5 times, again, 0.5 squared. And so just like body 1, that's 1.6 repeating. And now the free body diagram. We have the weight coming from the middle, 49.05. Up here we have the force on 3/2, and I'm gonna, since we already have F23, I'm gonna write that as negative F23. And then we have this force here that isn't gonna come into our equations, but RC. And then finally we have the clockwise couple of 100 Newton meters. Our about point is at the fixed point. So I'll start with RC. Rho is 0. Force is RCX, RCY. Cross product is 0. Then I'll do that couple, I guess. For couples, you don't worry about the force or the about point, and this is just a couple of negative 100. The weight force, the row vector is negative 0.433, positive 0.25. The force is 0, negative 49.05. And the cross product is, that must be the 21.24. And then last we have negative F23. The row vector is negative 0.866, 0.5. Force is negative F23x, negative F23y. Cross product is 0.866 F23y plus 0.5 F23x. since there's a fixed point, we only want the moment equation. So we have negative 100 plus 21.24. Yeah,
Wouldn't it be minus 0.5 F2PS?
it's this times this minus this times this. So you get the plus 0.866 F23Y plus 0.5 F23X is equal to the moment of inertia times the angular acceleration of body 3. And so our fifth equation says 0.5 F23X plus 0.866 F23Y minus 1.6 repeating alpha 3 is equal to 78.76. Okay, and that's our first 5 equations. But we have 9 variables, so we're going to need 2 vector constraint equations, 4 constraint equations. Did anybody get every single thing they wrote wrong? Okay, good. That's good. That's moving in the right direction. Any questions? That's it for today.